Hi, everyone. We're going to talk about faster objects and arrays in Java. I find it hard to give this a good title. And the subtitle here is probably a good description of what this project is attempting to do. Java is fast. It's actually pretty fast, really fast compared to what people think it is. But there are some inherent things about the language, what you can express in it, that makes certain things inherently slower with Java than they are in some other languages like C, C++, things that give you a little more layout control. And Object Layout is a project that aims to close that gap. And I think it's actually the only remaining inherent gap in speed between Java and C-based languages. When I say the only inherent speed gap, I'm not saying that this is the only gap in speed. I'm saying it's the only one that is inherent to the structure of the language and to what you can express in it. We'll get into some detail. This is a forward-looking talk. This is stuff we are proposing to add in a future version of Java. But there is working code with working proof that it actually does what I say it does. So we're actually very hopeful we can put it into a future version of Java. I think Java 9 will be somewhat ambitious, although we're still going to try, but Java 10 I think would be a good target. I'll talk a little about me and then get to the actual subject. My name is Gil Tene. I'm the CTO and one of the co-founders at Azul Systems. I've worked on lots and lots of things around Java for the last couple of decades and lots of other things as well. One of the things probably people know me a lot for is garbage collection. At Azul, we solved garbage collection. We think it's done. We solved it, so you don't have to, and that's it. We have a very think different kind of approach. Everybody's been doing that for 20 years. We went the other way, found a solution, so you don't have to do any of that anymore. But that's not the subject of the talk here, except to say that I like to play with garbage collection. For those of you who've seen some of my talks, I apologize that I keep using the same picture, but it's the only cool, funny one that I look younger in that I know. This is a trash compactor in my kitchen. It wasn't working. I had to fix it. The job of a trash compactor is to perform minor GCs during the week, so the full GC, where you pick the bag up and have to go outside in the dark, only happens on the weekend. In this case, the compactor was broken. The defrag function on it wasn't working. And those are fragments that were stuck in it. I had to fix to get them out and compact it and all that. I thought it would be funny to take a picture with the actual GC book at the time. And this was 11 years ago. So I've been thinking that's funny for a while. Beyond garbage collection, I've played with lots of other things. I've built virtual machines and physical machines, helped design CPUs. Operating systems, drivers, kernel stuff, firewalls and switches, and subscriber management systems that manage millions of people. And basically, we had to build our own app server in the late 90s because that wasn't around yet. You know, all kinds of stuff up and down the stack. So I've made a lot of mistakes, and I've learned from some of them. One of my favorite things to do is go around telling people how bad they do stuff. About measuring latency and response time, and that's another subject I spend a lot of time on, but again, not the subject for this talk. What we'll talk about today is Object Layout. This is a project that we started a couple years ago. We first presented this at the JVM Language Summit 1 year ago. And it seems to be a popular subject since, so I've been bringing it to developer forums more and more. Object Layout is basically about matching the speed benefits of C in Java for the specific things that have to do with memory layout, with the layout of memory and speed that comes from or that hurts because you don't have the right memory layout involved. We want to expose the benefits of memory layout to Java in a natural way, to regular Java objects, not to some new syntax that only works for new code. So this is an approach that's very holistic for all of Java rather than other things. And The idea here is to look at speed, nothing else, just speed, for regular Java objects on the heap. This is a mantra, which is why I'm saying it's slow. It's speed for regular Java objects on the heap. And I'll repeat it a few times in the next couple of slides, because the next couple of slides are going to be about what this is not about. This is what it's not about, okay? In the context of object layout, we could care less about footprint. I am not trying to reduce the footprint of memory. I'm not trying to save memory. I'm not trying to pack bits together or bytes together or get a few more words into a cache line. This is not what it's about. I'm purely looking at speed, not at saving memory or saving other work. This is not about off-heap solutions. I already mentioned that garbage collection is simply a solved problem. It's silly to waste engineering time trying to work around it again. But yeah, I understand other people still want to do that. This is not what it's about. It's not that it's wrong, it's not that it's right. Object layout is about speed for regular Java objects on the heap. Do what you want off the heap, but not with this. And then it's also not about immutability. Immutability is really cool. You can do immutable stuff with object layout, but you can also do immutable stuff. This does not have a mutable, immutable religion in it. Okay? And it does not come with the, if you buy into the immutable way of life, then this is good. Or if you have tiny little structures, then this is good. So all these are not good or bad. They're just orthogonal. They have nothing to do with what I'll talk about today. And there's a reason I highlight this, and that's because for the last couple of years, every time I raise this subject, people say, oh, you mean like value types, or you mean like packed objects, or you mean like one of those things. So I find myself explaining why it's not like that. And here we're going to explain why it's not like that for 2 or 3 slides, then stop with that, okay? So the relationship to value types is 0. Value types are really cool. I can't wait for them to be there in Java. I want to use them for so many things, but this is not one of the useful things you could do with value types. It's also got no relationship to packed objects or JNR or FFI, which have their own very good use cases for various things, like calling any native library without having to write wrappers, or efficiently dealing with memory that is not on the heap, like graphic card buffers or communication systems. Not that, and not a concern here. This is laser focused on the problem. And what's the problem? Speed for regular objects on the heap. Okay? So there's no conflict between this and other projects. You can do both. There is almost no overlap, but some overlap always exists. You can, for example, do some things in value types that you can also do in structured array and object layout, and you can also do with packed objects. But that's the same as you could use an array list and a hash map to store objects. There's overlap there. That doesn't mean that it's wrong to have the overlap. They just have different qualities and purposes, and you just want to use the right tool for the job. A pictorial way of this, looking at this, more of a Venn diagram. There's value types, object layout, and packed objects, JNR and FFI are grouped together. If we look at what they are and what they're for, value types are for on-heap stuff, only on-heap. They are very useful for on-stack things, passing parameters, getting return values that have more than one thing in them. Don't you wish you had that forever? Tuples. You know, they're very, very useful for that without having to create objects, not just from a syntactic point of view, but from a work point of view. They're very good for that. Great for that, in fact. I believe that value types will be amazing for on-thread, local thread operations, up and down the stack parameters and the rest. Little things that you pass around the thread as well, but once you put value types in the heap, they have interesting limitations. Value types are going to be immutable. The Java notion of value types is not, say, the C# notion of value types. They're very different things, and that often leads to confusion. Value types in Java are going to be immutable things that need to be changed atomically. So if you cannot see a partial value. If I replaced your immutable thing, you see the new immutable thing. When on thread without concurrency, that's a very easy thing to do. When you start putting on a heap, you start running into issues like, wait, word tearing. I have 5 words. I write the thing. Can somebody see half a word? And that's not allowed. And there'll be interesting solutions to that. Some of them will involve just boxing the value types in Heap or synchronizing them in some weird way in the JVM. We don't quite know which it'll be. But value types are going to be great, not in the heap so much, but in the parameters that we run around the stack. Packed objects give you precise layout control on exactly where things will be within a structure of data, an object of bits, and give you that to a very fine degree. And there's a really, really good reason to do this, because sometimes you talk to things that are not Java. And TCP likes to have the protocol byte here. It's not up to the JVM to decide where to put that. You have to explicitly lay it out. Whenever you're dealing with some other data structure, with something other than Java, you have to describe the layout of the actual memory you're communicating with and the structure of it, and many, many ways to do it. Packed objects is a way to try and express that from within Java in a systemic way. Now, it does that very well for off-heap. It actually has an on-heap version. And the common use cases are there. Object layout is speed for objects on the heap, right? Now, one key differentiator is going to be this. With value types, it's going to be for new code. Once you have value types, you write new things that use value types. And only other cool things that know how to read value types can look at your new things. So this is only for new code, right? Packed objects, same thing. With object layout, we're looking at doing this for POJOs. We're looking at letting these things participate with things that were written 8 years ago and could take one of these things, could take objects that are in one of these things. They already know what to do with them. There is no special need or special understanding or limitation on what you could do with it. You want to lock that object? Go ahead. I don't know if it's a good idea, but you could. You want a hash code on that object? Go ahead. No limitations. It's a full-blown Java object. And its members are that too. Okay, that was a lot of what this is not, and please don't confuse it with others. There's the overlap, an array of small footprint things, right? Immutable values especially. But let's look at the origin and why this is actually being done. This came out of an argument. Actually, Martin Thompson and I had a long argument. He reminds me that we sat in my car outside of his hotel until 2 a.m. And the argument is a common one. It's not the first one I've had it. It's not the last time we'll have it. It goes something like this. On the one side, you say we really need structs in Java. Why? Because look at all the stuff that high-performance people end up doing to Java or with Java just because we don't have them. We build these off-heap byte buffers or in-heap byte arrays, and we run these flyweight things on them with cursors that make something look like an object with an API, but actually its bits are spread across different arrays or within an array. And everybody does this themselves because there's no library for it, and there's no standard way to do it, and the compilers don't understand what you're doing, so they're not optimizing it as well. We just need structs. Just add structs to the language. It's a natural thing, right? And I think that's a pretty good argument. But I like to be contrarian, so I came in with this, Let's look at this. We actually have something that's a struct in Java. It's called an object. It's a struct and then some. It should be able to do everything you want in a struct and more. It shouldn't be less. There's nothing inherent to an object that makes it weaker than a struct in what you could do with it. What we're actually missing is the right speed semantics to let your code go fast when it deals with those structs, and that's what's actually wrong here. So Martin and I like to argue, and then we like to actually figure out who's right. And I think neither one of us was exactly right, but Martin took on the thing of let's try to code this, and then I took it over from there. And we basically started coding code in Java to see if we can capture semantics right. And I came with the notion of exposing the enabling semantic limitations that give you speed as the key thing we were looking for in that code. And it's not about adding features, it's actually about taking them away so that the result would be legitimate to optimize in certain ways. It's the fact that we have too many options in certain data types that prohibit certain operations. And I'll get into specifics here. Where does speed come from, or the speed we're interested in here? C layout has two dominant factors that give it speed. The first one is what we call dead reckoning. The ability to get to some memory location without having to jump through other references on the way there. So for example, when I go in an array of struct to struct number 17 field X, I don't have to go to a pointer. I just know it's 17 times size plus X, and it's right there. Right? So you can dead reckon to the address without hopping through memory. That's a huge speed boost, both for random access and non-random access. The other one is streaming. If you lay out an array of things and they are strided correctly in memory, then prefetchers are going to do an amazing job for you. They just run ahead of you. If you have any kind of access pattern, you don't even have to say it's there. CPUs will detect your stride and run their 3 different prefetchers the right way for you. And what's actually happening there is the CPU will burn bandwidth to reduce your latency, and hopefully not burn a lot of bandwidth because you really were going to use it. So while memory is hundreds of cycles away, when you know that the next 17 operations are also going to do the same thing, they're all in flight on the way to you, and when you need them, they're already in your cache. That's what streaming gives you there. Now, both of these come naturally out of flatter memory structures, and they're natural to express in languages like C. An example of that limitation can be seen in the difference between object arrays in Java and arrays of struct in C. Their syntax is somewhat similar, but one of them is inherently faster. Let's look at the actual semantics of what this means. In Java, an array of objects is a mutable array of same base type objects. Mutable because I can replace any member anytime I want. I can deposit a new object, a different object at cell number 5 than there was there before, so I can mutate what is in the array. And same base type because the base type here is object, but you can make an array of points. That tells you there are points in there, but they can also be subclasses of point in there. It's an object-oriented language. And as a result, we don't know what the size of a point is in an array. In C, we have an immutable array. It's strange to hear immutable and C together, but it's an immutable array of exact type objects. It's immutable because element number 17 in an array of structs is element number 17 in an array of structs. There is no way to replace it. That's what it is. You can mess with its content. You can mutate what's in it, but not what number 17 in an array is, which is why you can compute its address from the array address. It's exact same type, all the structs are the same size, which allows me to figure out that number 17 is 17 times size. If I didn't know what the size of each element was exactly, there's no way to compute the address of number 17. Or no good way, no easy way. Mutability and non-uniform members are what hurts both the dead reckoning and the streaming capabilities. The reason we have the no speed capability to match here is because both of those are options in Java. We don't know they're not happening, so we actually have to assume they might be, and we have to actually find and follow the reference to number 17 rather than compute it. An example of capturing the semantic limitations is here. A structured array of type T, this is a Java collection in object layout, is an immutable array of any Java object, as long as it's constructible. Now the object could be mutable or immutable, that's up to you. It's very common for them to be mutable in actual use cases, but they are exact same type, right? An array of points is an array of points, not an array of subclasses of points. And that's very simple to capture by simply saying you can make one of these, you can get elements from it, but you can't put anything in it. If you can't put anything in it, you can't change what the classes are, and you can't mutate it. When you create it, you say what type it is. It'll go ahead and make all the members of that type, but they're not going to change later. That's a simple example of capturing the limitations, and once you capture them, that collection can be optionally, depending on your JVM, laid out exactly the same as an array of structs would be because it's valid to do so. It's no longer wrong to do it because there's no way you could change where number 17 is, so it's valid to do it that way. That's an example of this. Now the target forms that we looked for object layout are 3. They're commonly used cases for laying things out. I just described an example, an array of structs. A struct inside a struct is another common thing, a flat structure rather than an object that points to another object. And the last one is a very common one in messaging, communications, other things. It's a struct that has a dangling array off the end, variable size dangling array, a message, a string, things like that, right? Now, you can express the equivalent logical relationship of every one of these in Java today. There's nothing that stops you from modeling this. But you can't match any of these on speed in Java today. We can express them, but our expression has too many cool options like mutability and different sizes, and that means the layout is not going to be flat. It's going to have references and dereferences in it. And we're going to capture all 3 of these with object layout. So the starting point has some rules in it. We actually tried to look at this as something we want to adopt into Java, the language, or actually, as you'll see, not the language, Java, the spec. So we want to capture all these semantic limitations, create the right data structures for them that give us the right contracts. And the theory is that we could do it with 0 language changes. So not Java the language, but Java the spec. We want a library in Java that has these semantics. If you use them, JVM knows what it is, and we'll make it go fast. So we'll capture this. It'll work vanilla on any JVM, starting with Java 7. I initially targeted Java 6, but as you'll see in some of the code later, Java 7 has some features that are useful for helping construction and visibility. And then we want to have JDKs have the option to say, I know what this is, I'll lay it out right, and I'll make it go fast. That's an option. It's not required. The code will work the same way either way. In fact, the vanilla and intrinsified implementations cannot behave differently except for speed. The idea is to capture the spec of the data structures, not the underlying behavior and implementation. But the spec needs to be carefully selected to enable optimization. Right now, we have a spec that prohibits optimization of these layouts. So the model for this is probably the most successful external contribution to Java in its history, Java util Concurrent. Similarly, started with Java sucks on certain things. Let's change that. Came from outside of Sun Oracle, Doug Lee and friends. And it captured the semantics that allowed good concurrent operations. How many of you used Java util Concurrent before it was called that? So you know what I'm talking about, Ed, Uni, Oswego, some people still have that code around, right? So you capture it, and then you don't make language changes, you just have libraries. Java util Concurrent to this day does not have any language features in it. Right? It's just a library. And you implement it in vanilla code. It might be slow. I mean, you can do an atomic long compare and set with a monitor, with a lock. It's not fast, but it'll work and it'll do the right semantics, right? And then you teach JVMs that, that's what it means, let's make it go fast, and that's one instruction. That's up to the JVM to optimize. And one important thing is you move that into the Java namespace so it'll be stable, so JVMs can really know what it means stably. And you also get safe access to things like unsafe under the hood that allow you to implement it with speed rather than require you to implement. I look at that as a model. We're trying to do the same thing here. In structured array, we'll try and follow the same rules, right? No language changes, vanilla implementation, and then capturing semantics so that JVMs could intrinsify them. We talked about this form, and structured array is the next deep dive we'll go. I want to go into that structure and explain what it is exactly. Structured array is just a Java collection for this type. It feels like an array, so that's why it's called that. And structured because we didn't find a better name. It might be a wrong name, I don't know. But We could just say array T, but then it'll confuse people. It's a collection of objects of type T. Everybody that does collections in Java or read generics should know what that is. It's arranged like an array. So you can sort of assume that it's got, a good get index that doesn't have to walk a linked list. But, that's an implementation detail. The collection is immutable. You can't put in it. It's got a get, right? And you can't replace elements, right? And you instantiate it with a factory. So when you make it, the collection and everything in it was made like that. That's kind of a requirement if it's immutable. It's hard to do it other ways. And then all elements are constructed at instantiation time, and you can't touch them later. Now the interesting thing is when you look at how to actually offer this and look at use cases, you come up with all kinds of cool ways people want to instantiate things inside. Because I have an array with 1,000 elements. They're going to be constructed when I instantiate the array. How should they be constructed? So yeah, there's the easy, use the default constructor in everybody. Yeah. But what if you need to pass them parameters? What if they have final fields? What if their values depends on their context, like their position in the array? So all these things are taken into account and supported. We have this thing called a constructor and args that we created to do that. And this is an example of context-based creation of an array. Suppose I have this class doof, and it kind of knows what its index is in a container, because it wants to, right? I don't know why, but it wants to. And here's how I create, I get the constructor and I want a length of 8. And here's the code. This is strange, it rolled off the bottom. Okay, here's code. I think there's a missing line there, but okay. Here's the code for actually instantiating this array. There's a bunch of spelling here, hopefully not too crude, but I'm making a new instance of structured array. And actually this should have been the mock structure. Yeah. But over here, we're basically, based on this context, constructor and args will use that constructor and the index of the context as a parameter to this so that they'll know what to initialize for in a final variable in the member. That's an example of the kind of weaving you might do. I'm showing it to show you the level of complication you could add if you want. It's not this complicated if you don't need to pass context-based stuff into your members. But you can. We're trying not to limit what you could construct in there. A very important quality of structured array that took a lot of design thinking is liveness. When you have a collection, and remember, we're trying to keep it all together in memory, right? So it'll work right, is this. When we started this, we thought that basically if you have anything alive in a structured array, the structured array would need to be alive as a result. And the reason we thought that is that's how every runtime that implements inner pointers to structures actually works. Every other runtime we've looked at. So if you, in any runtime, not Java, but others, have some bigger structure and you allow a reference to a field in it or a reference to a member of an array, that inherently keeps the container thing you point into the middle of alive because it'll be a problem if it isn't. So we started from that design and looked at how do we support that under the hood, what are the semantics that are needed. It gets very complicated. And then how do we tell programmers that this is happening and stop surprising them and all that. And we were about 3 or 4 weeks into thinking about this when Michael, one of our GC guys, kind of said, remind me again why we're trying to keep the array alive? And the answer is, because that's what everybody else does, isn't a good answer. It's why do they do it? And it turns out that the reason people do it is because that's the only thing they have liveness on. If you point to an integer in an array, an integer doesn't have liveness. So you need to take the closest thing that has liveness to keep that alive. You point to a member of an array, a struct and all that. But our members are objects. And objects have liveness already. And more than just having liveness, they have intuitive relationships to their collections. So a structured array is just a collection. It's not something new and surprising. A collection keeps its members alive. That's always true. But the members don't implicitly keep the collection alive. It would actually be surprising if I made a big hash map kept 1 million things in it, let most of them die, but one of them's alive, and I still have the 1 million things alive because that one thing is alive. That would surprise a lot of people and hurt a lot of performance, right? So that would be bad behavior. Structured array doesn't have that bad behavior. Under the hood, implementations will do all kinds of things to try and keep this together, track whether or not it's contained, and move everything together, but that's an implementation detail. When you're thinking about this, it's no longer a weird thing to think of, it just naturally falls out. You know what collections behave like, they feel like collections, there's no special rule here. The benefits of this liveness is, well, beyond intuitiveness. It's also fast and easy to optimize for. About 90% of the work we thought we had to do was gone the minute we decided this. We thought we'd have to teach things how to do this relationship. Well, collectors already know how to do what we need them to do mostly. There's some things we needed to add. And then, you know, because they're all regular objects, all the rules can be applied to them. We don't have to limit what you could do with them. So locking and hash codes and the rest of this stuff are not something we have to rethink, which goes into that you can play with 8-year-old code. You know, you could give your structured array an object to somebody. You can give a member of your structured array as an object to somebody. You could take a structured array and use a linked list that goes through it. You can index your structured array 15 different ways with whatever you know how to index objects with. And it just works, and it's not surprising, right? So natural, right? That's one of those things where once it happens, you know it's right. And until then, we thought, you know, we were working hard on the wrong thing. Okay, some more things about structured arrays. Small detail. Hopefully this will make you happy. We thought, you know, it's a no-brainer, right? We shouldn't even discuss it. Nested behavior is supported. You can have multi-dimensional arrays. And the non-leaf arrays are themselves arrays. So for example, a structured array of structured array, you can take a member of the outer structured array, and that is a structured array. It's an object you could pass to other things. You could take your rows and index them, for example, right? Or whatever it is you do with multidimensional stuff. It's also subclassable, which allows a lot of interesting code patterns we think are missing. And we'll get back to that. And very importantly, it's not constructible. Now this is not because we think people don't want to construct it, it's because to allow the semantics we need, we couldn't make it constructible. In Java, when you construct an object, anything other than a primitive array, the constructor is constructing something of a fixed size that is known from the type and with no arguments. The constructor later puts stuff in that object, but the constructor, if the constructor figures out later how big the thing is, it can't affect how much was allocated. A factory doesn't work like that. A factory could be told things and it'll go allocate the right size and then put stuff in it. So we had to use a factory semantic. I showed you what it looks like there. It's not that strange, but there's an interesting contradiction on the screen here. Has anybody noticed this? We have a subclassable class that is not constructible. That took me a little while to figure out how to do. Because that's a contradiction. To subclass, you have to expose a constructor. If you don't expose a constructor, nobody can subclass you. But we don't want subclassing to happen. And the cool thing here, and by the way, this might be useful outside of the project if you guys have a need for subclassable, non-constructible things, is something I call constructor magic. It's actually implemented under the hood, and it works on the following trick. Remember, we need vanilla and intrinsic implementations to work exactly the same way, and I cannot let you construct a structured array. So I can't let you do something in vanilla that I couldn't do in intrinsic. But that doesn't mean I can't let you write a call to a constructor. I just need to make sure that will never ever work on any implementation. And then I never have to deal with it. So the implementation does have constructors, and you do expose them, but if you attempt to construct a structured array, the base class would throw an exception at you. The only valid path for constructing a structured array is one that comes from within the factory, and there's constructor magic under the hood that keeps track of that. makes it impossible to break, or I claim it's impossible to break. Welcome you checking it. Okay. I need to hurry up a little because of time here, because I think I have about 7 minutes or less. Optimized JDK implementations. Basically, we'll need to track a new concept. That new concept is contained in container objects. You don't need to know about them, but the actual garbage collectors in the heap need to know about them. A container object is an object that has other objects inside and moves together. From a given contained object, you need to be able to walk backwards in some way. There's 17 ways to do this, depending on implementation, to find your closest container and then walk beyond that if you do. And the main thing this is for is that if the garbage collector ever moves anything that is in the container, it needs to move the entire container together, or we would need to compute addresses differently and break all the code. So that's what this is for. It's all under the hood stuff. Turns out to be very simple to implement in every garbage collector we've looked at. And we actually have an OpenJDK parallel GC implementation. We've got a Zing implementation, but we've looked at other collectors and we haven't found one where this is a serious challenge. It's not zero work, but it's not a new concept that's hard to deal with. In addition to that, there's some optimizations needed. Streaming actually comes for free. Once you lay it out right, streaming, yay, you know. But dead reckoning needs a little more compiler support. So we don't have to dereference to get to element 17, right? Because there's a way to compute it. But this is the way to compute it. So that's semantically the address of element X is the index times the element size plus the array plus the body size, because it's subclassable and this could be any type. Well, these two things are not constant. So I need to go get them from the array. That's technically as bad as dereferencing. Right? Not necessarily for each point, but still. Luckily, there are various optimizations that I call analogies to class hierarchy analysis and to inline caching. It's not the same thing, but it's like the same thing that JIT compilers commonly do, where they say, well, yeah, but if this type of structured array only has points in it, in the entire world, I can prove the size. So one constant goes away, right? And if it doesn't, the array doesn't have any subclasses, I can prove the body size, and then I get constants and I get the folding out. Some of these, in the implementations we have, these two optimizations aren't there yet. We just have the intrinsic get. So there's some more details somewhere else about this. The other two, I'm going to go through really quickly. Structured array is probably the best example to look at. One is struct instruct. I call that an intrinsic object. Intrinsic, not in the sense of compilers, but in the sense of English. So, you know, if an object instance is intrinsic to another object, if you look it up in the dictionary, it means they were made together. They had a strong relationship to each other. That's what the language says, not Java, the language. This is how you say that in Java, now, in vanilla. You put an add intrinsic, and see, that's just a regular private final something, but it's annotated with an intrinsic, and it's initialized with a factory. There's a little cumbersome spelling here. I wish we didn't have to pass any of these parameters. Some Java version with a language change might allow us to save some spelling, but these are just to make it so we don't have to change the language. This lookup thing right there is why I need Java 7, because Java 6 doesn't have it. We are going to look at a private final field, which by definition requires stuff for security, and we didn't want to break all security because we want to actually move into the core libraries, so we needed to do a way to secure. And there's some details about surviving silly things like reflection overriding final fields and how do we do it safely. And the reality is you can't do it safely, but you need to detect it and de-optimize your code and run like the old stuff without the optimization if somebody was silly enough to write over a final field. A struct with an array at the end is modeled this way. You basically subclass an array. Subclassing is a simple way of modeling a struct that has something else after. So the struct with an array at the end is just a, you know, for primitive arrays, a primitive array of longs is just an array of longs with whatever else you put in the subclass. Semantic capture what you need. And that goes all the way to primitive references or reference arrays. Structured array is subclassable. So a struct with an array of structs at the end is captured through structured array already. Same semantics. Okay. We talked about the forms. These are the three forms and their parallels. These are composable together, which turns into really cool stuff we didn't think about when we started. So I like to use this picture a lot. You have the heap. In the heap, you can have a structured array of foo. Inside, there's a structured array of foo. Foo might have two intrinsic member, bar and doof, and bar might be a constant length structured array of moo. And this is a completely flat data structure, right? This is an example of putting it together. An octagon could have a constant length structured array of points. In it, flat, not dereferenced. The structured array of points itself is naturally going to be flat of points. This is how you go and get a point, natural syntax. You can then have an octagons type that has many octagons in it, again, flat. And here you have, let's get point x of octagon number 3, point number 7. There is not a single dereference in this line. From the address of octagons, I can compute that without going through memory. And that's the power of putting it all together. Composability is cool. These iterators are also optimizable. They don't have to go through memory. There's not necessary next there. They're just an increment of a reference. So no dereferencing every time. Status-wise, because I am short on time, well, I'm a little over time actually, there is vanilla Java code up on GitHub that works, has tests, and actually has little micro benchmarks for it. Written in JMH, so they're valid. Well, written in JMH. It's fairly mature, and we've worked out a lot of spelling stuff. There's still here and there questions about should we have variants that are only protected subclassable arrays so you don't have to expose your gets to your customers, stuff like that. There is an intrinsified implementation coming soon for both org.JDK and Zing. Coming soon meaning it's actually on my side to actually write up the JEP and stuff and propose it to OpenJDK. Some early numbers look good. For example, a hash map ported from OpenJDK 8 to use a structured array as a spine rather than an array of nodes as a spine is between 5 and 12% faster on hash map get. That's without you even knowing what structured array is. It could do that. And the next steps are to try and do actual project work with it. The aim is to put it in some Java version in the future. We will be looking for support, hopefully from people here and elsewhere. And the really simple summary is here. New classes, no language changes, works in vanilla on any Java version 7 and above. The go fast is an option that we hope everybody will take over time. And with Zing, we absolutely intend to make it go fast even with Java 7, so you don't have to wait for Java 9 or 10 to get the speed. And with that, how does the Q&A part of this work? When is the next actual talk? Is it 11:50 or 12? Oh, well, that's great then. So what I'm keeping you from is not a next talk, it's lunch, which means those of you that are actually hungry can go eat, but I'd be happy to stick around as long as people want to ask questions and talk about this. Thank you.